Quantum computing is an emerging and exciting field. It has the potential to solve computational problems that are beyond the reach of traditional or classical computers. In the future, quantum computing could transform areas such as chemistry, finance, drug discovery, and more. Researchers who want to experiment with quantum computing and develop quantum algorithms and applications unfortunately face numerous challenges. Getting access to different types of quantum computing hardware has been difficult. Running simulations of quantum computers can be expensive and complex, and development tools are often tied to individual technologies. Amazon Braket overcomes these challenges by providing a fully managed quantum computing service in the cloud, so you can more easily explore and innovate in this emerging field. Amazon Braket enables you to design and build quantum algorithms with technology-agnostic tools in your own development environment, or by using Braket's managed notebooks. You can test and debug your code with local and on-demand high-performance simulators. Then, with Braket, you can run your code on actual quantum computers, choosing between different quantum technologies from multiple providers, so you can decide which one best fits your applications. You can also build and test hybrid quantum algorithms, combining quantum hardware with the classical computing resources of the AWS cloud. Amazon Braket's pre-built examples, tutorials, and tools will help you get started quickly. And our partners and consultants are here to support your journey. Step into the future with quantum computing and Amazon Braket.
So good morning, everyone. My name is Vanessa Hernandez. I am a senior solutions architect at AWS in Mexico City. I attend public sector here. And I am part of this group of quantum enthusiasts that have the mission to deliver the message of what is quantum computing and what is AWS doing in this field. So I'm really happy to be with you this first day of the workshop. And I have two disclaimers for you. The first one is I am not obviously a native English speaker, so I will do my best to deliver an understandable message to all of you. But at any point, if you're not getting something or my English starts getting weird, just let me know if you need me to repeat anything or you need me to try different words to explain some part of the content. The second disclaimer is we have very varied backgrounds in the audience. So we have people that is just starting, people that has a little bit more of experience. So for those that are getting the first steps into quantum computing, don't worry because we are going to be moving step by step. In fact, this first day is really introductory messages, is really simplified concepts. And gradually, during the next 2 days, we will be moving into more sophisticated content. So that's for the people that has more experience. Please be patient. We will get there. We will get to talk about noise, about quantum annealing, about quantum machine learning, but we are moving gradually so that everyone has the same starting point and everyone has the same understanding moving along the content. Okay, so let me talk to you about the agenda that I have for you today. This covers the part that I will be delivering. After me, Juan will be delivering also some topics regarding noise and things like that, but this is the first part of this day one. So I will be there will be lectures and there will be hands-on because we don't want you to get bored, and obviously we know you are eager and you want to get into the console and look at Braket, start working with it. So we try to combine the lectures and the hands-on exercises so that this becomes a very interactive workshop. And actually, the presentations are not so long. So I hope this will get us all involved the whole time, okay? I will give a really brief introduction about quantum computing. It will be actually just 3 slides. So for those that have more experience You might think, okay, explaining quantum computing in 3 slides is kind of a challenge, but we are just delivering here a very simplified message. It's just an introduction for all of you so that we all can understand what it is, what is it about, and why it is relevant. Then we are going to start preparing our Event Engine accounts. Event Engine is a tool that we use for this type of exercises. So you will be accessing real AWS account, but you don't have to worry about paying for the use of those accounts. Those accounts are temporary, so when we end the workshop on day 3, they will be erased. But they have, you will be having full access to the functions of Amazon Braket, and is kind of a sandbox. Okay, so even if it is a full a full AWS account, for some of the services there are certain limitations. It's not the case for Braket. We can use almost all the functions, I think, and you will be receiving those accounts in a few minutes. Then I will explain what is the AWS strategy around quantum computing. We will take a break, of course, and we need to take these bio breaks at some point. And then I will go into an introduction of Amazon Braket. So before getting our hands on it, you will be seeing some slides. I will give some explanation of what are the capabilities of our Amazon Braket service. And point number 7 is a demonstration. So at this point, I'm sure you will be ready to get your hands on, but I really need you to be observers at that part. So since during the hands-on, during the actual exercise, I will be asking you to provide me some information that you will find in the console in certain menus. I need you during the demo to be observing what I am showing so that you get familiarized with the console before actually starting to use it. So that during the exercise, it will be more easy. It will be easier for you to find those pieces of information that I will be asking for. Okay. So this is our agenda. These are the topics that I will be covering with you. And let's get started to this introduction to quantum computing. So what it is quantum computing? Um, let's say it in a simple way, not getting into the physical and mathematical details of it. And in this situation, we can define it as an alternate way of representing and processing information, an alternate way to what we all know up to date, which is digital computing. So what quantum computing does is try to apply some properties and characteristics of the behavior of subatomic particles, which is actually described by quantum physics or quantum mechanics. And that is why it is called quantum computing. And actually, digital computing, which is what we know of today, is starting to be called classical computing, in a similar way that we have classical physics that explain the world that we can see with our own eyes, and we have quantum physics or quantum mechanics that try to explain the behavior of subatomic particles. Okay, so we're in the very first years of practical quantum computing. Quantum mechanics started to be studied and researched by 1920s approximately. So we have 1 century trying to find out about these behaviors and researching that. And more or less by the 70s or 80s is when some researchers, some specialists started to think of using the learning that they had about quantum mechanics and apply it to computing. But the first years, it was all theoretical. I mean, there were no actual and real quantum machines, quantum computers to test all those theories. So actually, it has been less than 10 years that the first quantum computing was published as I mean that was made available for the public through the cloud, which happened in 2016. That researchers can start working with actual quantum computers and can start testing all those all that theoretical work that has been done up to that point. So given that situation, that let's say that we are in those early years, there are still a lot of challenges to be overcome to be able to leverage the full potential of quantum computing. So these challenges might be related to the way that quantum processing units or QPUs are being built and how the hardware can be used to simulate the behaviors of these subatomic particles. It can be also related to the way we program these computers, because we're still learning how to manipulate these quantum bits, which are the minimal units in which we represent information, and how to overcome actually the delicate states that represent the quantum behaviors and that get affected even if we try to measure or to observe their value. So all those challenges, I mean, it's a field that is full of new ideas, of research, but it is the right time to get into it, because as soon as we start learning of quantum computing, we can contribute to generate this knowledge that is required. And obviously, we will be ready to start working or to get some value of these machines as soon as all those challenges start to be overcome in some way, okay? And the potential is huge for this new way of, or for this alternate way of representing and processing information. What we have seen with the available computers that we have right now, the digital computers right now can do is, I mean, we can do a lot with them. We have learned a lot of them, and about parallelism and about optimization of algorithms. But even if we have today's supercomputers and HPC clusters that can process really complex problems, there are still certain type of problems that cannot be solved by these machines, because it would take a lot of time for the machines to get a response, or it will take more resources than what those clusters have available. So in this graph, what we are seeing is we're talking of maybe hundreds of years that might take to a supercomputer to solve certain kind of problem, versus maybe minutes that a quantum computer might take to solve that same use case. This is, I mean, it's hundreds of years versus minutes in our graph, but in reality, there might be problems that are estimated to take even thousands or millions of years to be solved by digital computers, versus maybe we're not talking about minutes, but even if we are talking about hours, days, or weeks that might take to a quantum computer to solve those use cases, it is reachable. It is actually a human being can see the response of a quantum computer working on those kind of problems. So this is the potential. And as I said, since there are still so many challenges to build and to use quantum computers, we're still in the way to find actual and practical problems that demonstrate this quantum advantage that has been called by the specialists and by the people in the industry, okay? But that's the potential. So that is what we are expecting to see in the upcoming years, that quantum computers might offer to all of us. And what we can think is, since quantum computers are trying to use or to leverage properties related to the behavior of subatomic particles, we might think that maybe direct use case that are applicable to quantum computers are only related to chemistry or to simulation of physical systems. But the truth is that I think in any industry and in any sector, we can find problems that are complex enough that might benefit of the potential of quantum computers. So just to give you a couple of examples that are not necessarily related to chemistry or to biology or physical systems, if you think, for example, in certain logistics estimations and optimization problems, for example, when we have an airplane and we're going to use that airplane to transport packages. So there are algorithms that are used to optimize the way in which the space inside the airplane is used to position the packages that it will transport. And obviously to consider to, okay, I don't know, I'm receiving an annotation request, Juan. I don't know what exactly is that in, should I
Um,
decline?
I guess so, yeah. I don't know what that is. You can decline it.
Okay. I'm sorry, this is a function in WebEx that I don't know. But okay. So if we're thinking of this algorithm used to optimize the way packages will be put inside the plane, and also consider the weight of those packages to see how much fuel the plane will need. And then we will consider the routes that are available to the different destinations that are covered by this transportation company, and how to optimize also the route that the airplane will follow. So this optimization problem can get complex enough so that at the point when we add one more node that conforms the network of destinations that are reachable, the time it will take to process the optimization algorithm might start growing exponentially. So just adding one node will make the difference and take even a trend to infinity in terms of the time it will take to solve the algorithm or the use case. So obviously we're doing a lot of, or we are solving a lot of use of those use cases and problems right now with our digital computers, but because we're using simplified models in which we limit the amount of variables, we limit the amount of values that those variables can take. The same happens, for example, in financial services when we want to do a simulation of how, for example, the stock market will behave and how this will affect, for example, an investment portfolio. So again, the models that are available right now are limited in terms of the variables they use, in terms of the values of those variables, and that limits the precision of the result that we can get in our simulation. So those are examples that are really simple, but I wanted to mention those because those are not necessarily related with chemistry or with physical systems. It's part of our day to day. It's part of sectors that doesn't necessarily have a direct reference to subatomic particles, but that can benefit of the way that quantum machines represent and process information. Okay, so these are my three slides for the introduction of what is quantum computing and what is its potential. And what we're going to do right now is start configuring our event engine accounts. So I will do this along with you. I will be configuring an event engine account at the same time as you do so that you can follow all the steps live. And the first thing we're going to do, let me get out of the presenters mode, is to share with you this link. So that you can start configuring your accounts. Okay, let me access the chat here. Chat. Okay. There you have the link. Please open it. I will do that with all of you here so that you can follow the steps along with me. Okay, so this is the first screen you will see. At any point, if someone gets a message saying that all of the accounts are full and you cannot get access, let us know because we have other hashes we can provide to you. But at this point, I think we with the number of participants we have at this moment, we are covered with this link. That is not the screen I get. Okay, what are you seeing? Maybe you are seeing a screen like the one I have in this.
Yeah,
slide.
since you are going from WebEx, you will see first on a screen from WebEx telling you that you are going to an external website. That's okay. You can accept that, and then you will see the first screen that Vanessa is showing to you.
Okay. Enrico says I get terms and conditions. I don't know if those terms and okay, maybe you okay, so some of you might be seeing the screen that Juan mentioned, the one from WebEx saying that you're going to an external site. Just give next at that point in that button. If you see the terms and conditions, just say accept terms and login, the green button here. And then you will be able to see here the screen that gives you all these three options. Raul Palacios says he's seeing event not running.
Should be up in a second. All the event is launched. I'll take a look.
Okay. As quantum computing is based on quantum physics, there will always be uncertainty. That's true. That it's true. We will talk a little bit more about that in a while. Okay, a couple of the people is saying they are receiving the event not running message.
Yeah, it will be ready in just 1 second.
Perfect. Okay. Event is there, says Matthew. Okay. For this hands-on, will we try gates? Today we will be using gates. Tomorrow you will be using quantum annealing.
The day after tomorrow, we will be using quantum annealing.
Okay, the day after tomorrow. I'm sorry. Yeah, but you will be testing both types of machines, the gate-based machines and the quantum annealing from D-Wave. Okay, okay. Some people is getting ahead this step. Please wait a few minutes. I just want all of us to move together so that we don't get confused.
So I suggest, Vanessa, that you just focus on taking everyone at the same time through the steps and ignore all other questions, and I will answer the questions on the chat that are not related to the instructions.
Yeah, my only concern is the ones that were saying that they had this message of event not running.
It's all right. I see how people are getting in now. So it should be working again.
Okay, so if everyone can see this, just click on the OTP option. And please use a corporate email. You cannot use Hotmail or Gmail. It will not work for that. Use a corporate email. I will use mine here. And send
I
your
hate to correct you on that, Vanessa. I'm sorry. You can use any email you want. If it's Gmail, the one that gives you fast response, use that one. It's totally okay. There's no problem.
Okay.
I also want to ask you to please maximize your window and zoom a little bit so we can see clearly what you are doing, because there's a lot of windows open there right now, and it's clearer if you can zoom in a little bit.
Okay.
Just Control Plus or something like that.
Oh, okay.
Perfect. Thank you very much.
Okay, so use any email you have access to. Send your passcode. Here, it will ask you to introduce the OTP that you have just sent. So let me just check mine. Okay, those that are in the dashboard, just wait for a few seconds. We are all moving together. I'm just waiting for my OTP. Not getting the OTP, try the resend option to see if it works, and be
It might
sure
take up to 10 minutes to arrive. In some cases, I've seen people that takes up to 20 minutes even, but that's the rare case. What never happens is it never goes to the spam folder or anything like that. I've never seen that before, so it shouldn't be on your spam folder.
be sure you're typing your email correctly. When to spam in Gmail, yeah, just to be sure, check on spam because it
Thanks for
might.
that.
Okay, if you are there, sign in successfully. Okay, if you're there, yeah, please click on the AWS Console option. In here, I will ask you to take a couple of notes. So if you have a notepad or something, click on this copy login link button and take that login. It will be a long, I actually have here one. It will be a long link. Keep it in your notepad, keep it at hand, because if for some reason you lose connection, you can just click on that long, very long link and it will take you directly into this part, okay? Some people is not getting the OTP.
Let's just wait a couple of seconds, 1 minute more for everyone to have the OTP. If after 1 minute someone has not received the OTP, you can ping me separately and we can try to figure it out. You know that in the chat you have the option to talk to everyone, but you can also click on the drop-down list and pick my name and send me a message separately, and we can try to work it out.
Okay, so let me know by raising your hand if you are ready, if you're at this screen that I am showing. Okay, I see a lot of hands up. That's good. Very, very good. Okay.
Someone is asking as well if you can repeat, how did you copy the access link for later?
Okay, the access link, you have this button here that says copy login link. Just click on it. It will not show you anything. Just click on it. And then you go to your notepad and just do the control paste option and it will paste your link there.
Another note is that some people have very small screens. So in general, you can make your screen as big as you can. They will be able to see better.
Okay, I mean, I'm full screen apparently. I don't know if you're seeing it so small.
No, that's fine. So especially when you open the notebooks, try to zoom in as much as you can. Not just full screen, but zoom in to make the font bigger. That's all I'm saying.
Okay, it's less than half of the people that has get to this point. So
yeah, I think we can move on. Thank you, Vanessa.
Okay. Let's continue at any point. If you have trouble or if you feel lost, just let us know through the chat. Okay. Well, so here you're going to click OK. You're going to click an Open Console. I'm sorry, Open Console, which will take us to the actual AWS console of our event engine accounts. And at this point, before starting playing with Braket, we have to do some prep work, some initial steps that I will ask you to complete. So everyone should be seeing the home of the AWS console. Here, in order to access Braket, we have different options. You can do that from the services menu, and then you go to quantum technologies, and there you will find Braket. You can search it directly here in this bar. You will type Braket just with the K. It is not CK, it's just the K. references the direct notation, which is the one used to represent qubits, quantum bits. So get into Amazon Braket here. And before we do the prep steps, I have to mention that every one of you is with this link, with these steps that we have completed up to this point, each one of you has an individual access to these event engine accounts that we're providing. But each account is being shared by 5 people. So this will not affect your experience accessing the resources. What will cause is that at some points you will see there are more resources than those that you have created. I will let you know at which points you be careful on accessing specifically your own resources. And this is to avoid getting in conflict with, for example, modifying Jupyter notebooks in which
All
other
right,
people
Vanessa,
will
I'm sorry. This part we will need to go slower for everyone to be able to catch up. Before we continue, let's make sure that everyone is inside. So you have to select the OTP option, not Amazon or any other option, because the other options will not work. You have to make sure that in the previous screen, you select OTP. Otherwise, you will not be able to access. Till you click on the console button, you will get access to this screen that Vanessa is showing. And we also mentioned that you should copy the long link that is provided to you to access later. So I would like to see if you don't mind putting a +1 in the chat window who is not inside the AWS console right now seeing this screen. The ones that are not inside. 2, 3, 4, 5, 6. Okay. It's showing the screen even after putting OTP. Seems like quite a few of you. Let me check something here. We have plenty of accounts. More or less half of you are already, much more than half of you are already in. It's been that. Okay, I'm gonna explain in my window what we have done up until this point where Vanessa is right now. From here, I will have to continue with the event so we don't delay the rest of the audience, but I'll try to help you separately one by one until you get to this point. So appreciate your patience. I'm gonna take my screen for 1 second, Vanessa, just to show people that just got in. And apologies to everyone that is already there. This is only the first part where we need to make sure that we set up things. After that, we will go much faster. Everyone will be able to follow. After you receive your OTP and you enter into the window and you click on enter, you will be able to see a screen like this one. Here, the only thing you need to do is to click on the AWS Console button. And from there, you will see a button that say Open Console again. What we are saying is that it's good that you click on this copy login link. It's a very long link. You will not see anything when you click on it, but it will be copied in your clipboard and you will be able to paste it somewhere in a notepad. And it's going to give you access tomorrow and the day after tomorrow for the rest of the event without doing anything else. This is just direct access, this copy login link. After you have done, then you just have to click again in Open Console. And when you click on that, there will be a new tab. So the previous tab is still there. You still can refer to it anytime today. But there's a new tab that will open a fully working console. That is where where Vanessa is right now. The only thing she did so far is just to search for Amazon Braket and go to the main window in Amazon Braket. The rest is pretty much the same. So I'm gonna start now monitoring the chat and see who's still stuck. I'll do my best to help you, but we need to move on. So sorry, Vanessa, about this. Please continue. Thank you.
No problem. So hopefully we are there. And again, if anyone is having problems, if anyone is getting behind, write a message in the chat so that Juan can help you. Okay, let me share again my screen. Okay, there we are. So hopefully, again, when you hit the Open AWS Console button, it will take you to our main page. And from here, you will be accessing our Amazon Braket service. How do you do that? You can go here in services, you can go here to quantum technologies, and then you will find there Amazon Braket. You can also use the search bar and just type Braket with a K, just a K, and then you can click on this and it will take you to the Amazon Braket Management Console, which I will explain in a little while. At this point, we're not going to go through the menus. We just need to complete some initial steps so that in a while, after I complete the presentation, we are all ready to execute our hands-on exercise, okay? And I was telling you that you are receiving here individual access to these sandbox accounts, but each of the accounts is shared by 5 people maximum, okay? The effect that this will have is that at certain points you might start seeing resources that you have not created that are there because the other users are creating them. That will not affect your experience with the hands-on exercises. The only effect it will have is that you have to be careful on accessing your own resources. This is to avoid conflict when you, for example, are editing a Jupyter notebook that you are working on someone else's notebook, okay? But I will let you know when you have to be especially careful, okay? So, and I am mentioning this at this point because the initial steps that we're going to execute, the first one in your shared account, the first people that hits the button will receive a success message and the rest will receive an error. That is not a problem because we're just configuring some roles that need to be there so Braket can work and interact with other services in the AWS ecosystem, and some terms and conditions that have to be accepted so that we have access to the QPUs that are provided by third parties. Okay, so let's go do that. We need to go to this menu in the left side that says permissions and settings is the last option in the Amazon Braket menu. So click on that. And this is the first part. We have to accept the terms and conditions because we're going to be using third-party devices that are not created by AWS, that are provided by our partners, and that they provide these QPUs that are available through Braket. So click on the accept terms and enable. And again, the first person in the account that clicks on that will get the enabled check, and the rest might get an error here. Okay, that's fine. Don't worry. The second step we need to complete is in this second option that says execution roles. So click on that, and we're going to generate a role for Amazon Braket so that this service can use that role to access other resources in the AWS cloud. So just click on the create service link role, and again, the first people that clicks on that will get the service link role created successfully message. and the rest might get an error. Okay, so hopefully we are all there. I will ask you to raise your hand to see if you are here with me, please. I want to know how many of you are ready at this point. Okay, I see your hands here. That's good. Okay. Okay, this is stopping. So I think, I don't know if the rest are having some trouble getting into this point. How are we doing it? Do you see any comments having problems with this step one, or we?
I think we can continue.
Okay. Okay, so one more step we have to complete at this point, which is generate a Jupyter notebook. And I will talk more about what we will be doing with our notebook later, but at this point we need to generate it because it might take a few minutes and I don't want you to be waiting later on. So we will do that at this point. Okay, so in the left hand menu, you will see an option that says notebooks. Click on that, please. And then click on the create notebook button. We will use the defaults here. We won't change anything, but we need to give it a name. And I will ask you here to use a name that identifies you. It can be your nickname, it can be a special word that you have, but please make this name unique. This is one of the parts where you will, in the console, you will see a lot of resources, a lot of notebooks that will be created by the other people that is sharing the account with you. So it is important that we can identify our own notebook easily, and then we avoid conflicting into, messing up with the notebooks of the other participants. So I will use my Amazon ID here. You can use any word that you want, but please make it unique and make it identifiable. The rest of the options, you will leave them as they are. We will use the defaults and just click on the create notebook instance. Okay, and it will take a while. It should appear here, your name, your ID that was just created. And with the status, I'm sorry, but I have the WebEx boxes here, with a status of pending, and it will take a while to complete. So we will leave it up to this point, but make sure you have your Jupyter notebook already there listed. Okay, so hopefully we are there. Failed to create notebook, so we are receiving some errors, I think.
Let me see. Gonna check around. It's difficult for me to see in which account you are, but I'll try to. For those that getting the error of linked error, service linked role error, don't worry about that. And for those of you who already started to create the notebook, as is in status pending, that's normal, as the way it should be.
Yeah, pending is okay.
Let me see. For the people who are having problems creating the notebook, I will appreciate if you can ping me in the chat your account number. Your account number is, as you can see, if you can zoom in a little bit, Vanessa, people can see in the top right corner, you have your account number. Besides that, master key add a message. It says team role master key. Yeah, exactly there. If you can ping me that number, I can try to figure out what's the problem with those of you who are having problems launching the notebook.
Okay, so it is okay if it shows as pending. It will take a while. That is why we are doing it right now. So that I will get back to some slides, and while I'm explaining those slides, this will complete. But we all should see here our notebook listed in a pending status. If not, if you are seeing other things or receiving error messages, please let us know through the chat. Okay, in the meantime, I will get back to the slides. Juan, if you need me to pause because someone is having, or there is a general problem we should address, just let me know.
Thank you.
Okay. So, okay, I had these backup slides to show you, but we all did that step together. And now we're going to talk about quantum computing at AWS. So what is our strategy around this field? Okay, so our strategy, I mean, at AWS, we're convinced of the potential that the quantum computing has. So we are really doing a strong effort to have a strategy to help our customers benefit and get all the value that these technologies might provide in the near future. And for that, we are having these 4 components in our strategy. And at this slide, I will just mention them because in the upcoming slides, I will be explaining each of them. So we have our AWS Center for Quantum Computing, our Quantum Solutions Lab, our partner network with partners specialized in quantum computing, and of course, the star of this workshop, which is Amazon Braket, our fully managed quantum computing service on AWS Cloud. Okay, so what is the AWS Center for Quantum Computing? Well, this is a research center in which, as I said, I mean, there are a lot of challenges in quantum computing. We are in the very early years of practical quantum computing, and we at AWS want to contribute to this field. So we have this research center in which we are participating to investigate and to generate knowledge around state-of-the-art topics. So, for example, one of the lines of work that is happening in this research center is around how to develop better quantum hardware. And actually, we are developing a QPU, a quantum processing unit of our own, an AWS quantum processing unit. What you will see in Braket today is we have different vendors making their QPUs available through our console. But we are expecting in the near future to offer our own QPU. And what we know, and I mean, this was presented at our last reInvent event last December, is that it will be based in a superconducting architecture. We will see that there are different architectures for the QPUs, and ours at this point is being developed using a superconducting architecture. And another line of research that is being conducted in this center is around how to reduce quantum noise. And we will be talking more about noise in a while, but the thing is that the quantum states are so delicate that any interaction with the surroundings affect them. So even if we are just observing to see what value the qubit has, we are affecting it, and that creates noise. So there are a lot of efforts either on hardware development as in software to reduce that noise. Okay, so one of the research lines is also related to that. So those are examples of what we are doing at this research center, which, just as a curious note, is located near Caltech. Caltech has a strong quantum mechanics program. So, of course, we're trying to collaborate there with academics, not only from Caltech, but it is a strategic point to have the research center located there. And we have people such as John Preskill collaborating with us. John Preskill was announced, I think, a couple of years ago as an Amazon Scholar that has been collaborating with us around our quantum computing efforts. Okay. The next part of our strategy, and I must say, this has just been recently announced that is what I was forgetting. I had a slide for this. But as we have this research center for general quantum computing topics, we have just announced that we're making a particular effort around quantum networking. So, okay, when we talk about quantum computers and we say we are going to represent and process data in a different way using these quantum mechanic properties, there's also a challenge on how these states can be communicated through the network, right? Because current networks are digital, as our digital computers, but we need another methods, different ways in order to transmit the quantum states that we are generating in quantum machines. That is what quantum networking is focused on. And we have a particular group in our research center that is focusing on quantum networking. This is recently announced, but we are also giving a particular focus to this subgroup, let's say, or sub-specialization inside quantum computing, okay? Then the next part of the four pieces of our strategy is the Quantum Solutions Lab. The objective or the goal of the Quantum Solutions Lab is to provide advisory to our customers in terms of how they can develop a quantum strategy. So when one of our customers says, okay, I think I have a use case that might be candidate for quantum computing, we can work with them with a multidisciplinary team that help them review the use case and determine what is the best approach to solve it. It turns out that this approach might be still digital computing, because there are cases that are actually solved by HPC and digital computers yet. We have a lot of knowledge on that field, but it can turn out that it is a good use case for quantum, and then we can develop, or even we can combine and make a hybrid strategy where we use still digital computers for what they are really good for, and then quantum processing for those parts that are not yet solved by the digital piece. So this is the goal of our Quantum Solutions Lab: work together with our customers to check their use cases and then determine what is the best way to approach them using quantum and using digital. And what else I must say about this Quantum Solutions Lab? I think that's it. That's the goal, and that's and I must say the engagement of the Quantum Solutions Lab with our customers depends obviously on that our customers really want to do a serious effort around having a quantum strategy. Okay, and then we have our partners. So that is a third part of our point of view on the quantum field. So we are working together with different organizations around the world that are interested in quantum computing, that are specialized in quantum, that can work with our customers to generate these quantum strategies, or that are specializing, in some field. Maybe some of these partners are specialized in quantum networking. Maybe some of them are specialized on quantum resistant security systems. Some of them also are developing things and solutions that run on Amazon Braket. For example, some of them have IDEs, development interfaces that are drag and drop, so that it is easier for the developers to generate their quantum circuits, and that interact with the Amazon SDK to run the circuits on Amazon Braket. Okay, so these are just examples, but we have different partners doing different things, focusing on the quantum computing field, and this is also one of the parts of our strategy. And of course, Amazon Braket, which, as I said, is the fully managed quantum computing service available on AWS Cloud. And I will be giving you more details on this in a while, but at this point, I want you to mention. I want to mention like the four parts in which its features and functions are grouped. So the first part is we want Amazon Braket to enable you to build your quantum algorithms, your quantum circuits. And for that, Braket provides an SDK that you can actually install on your own computer and then start building your code there, start building your circuits. We, of course, provide the Jupyter notebooks, as we have just generated one in the Braket console, so that if you don't want to do the code directly in your computer because you need maybe more resources, you can use a managed instance on AWS and then generate your code there. And of course, you can also interact with Braket using the command line interface of AWS. The second set of functions that you can get from Braket is the possibility to test your code. And for that, we're providing simulators. And we have different types of simulators. I will be talking about them in a while. But the idea is that before you go directly into the actual QPUs, you can test your code in these simulators, refine them, optimize them, and then when you are ready, you can go directly into the real QPUs. And this is really good for cost optimization. So you have this possibility in order to start testing your code. Then, of course, the heart of Braket, which is the real QPUs, where you can run your circuits, and you will see that we're providing access to different quantum machines with different architectures, with different programming models, and you will have all of them available in a single pane of glass through Amazon Braket. And finally, analyze your results. So Amazon Braket is not an isolated service. It lives together with the rest of the AWS services that we have available. And you will see that some of these services will help you monitor how the algorithms are being executed, generate benchmarks, and know which is the best QPU for each of your use cases or for each of your algorithms. You will be able also to store the results of your executions and then use those results to generate maybe an analysis, maybe a dashboard, different things you can do with those results. Pass them to digital computers to do some kind of analysis, etc. Right? So this is like, again, the four big groups in which all the features and functions of Braket can be put together. And this is just the slide in which we give you the introduction to what this service is about. So in the next slides, we will be going a little bit more deep into Amazon Braket. But at this point, I think we are ready to take a break. We have just 1 hour of starting. So I think we can take how much time, Juan? Do you suggest 5 minutes, 10 minutes for this first break?
Yeah, we can take 5 minutes. Maybe, well, since it's already past, let's come back to 07. What about that?
Okay, let's see each other here at 07. Whatever your time is, I'm at 11, so 11:07. And we will start with our Amazon Braket details at this part of the presentation, okay? Okay, so I think it is flowing because I don't see recent messages about problems with the setup. Yeah, okay. Juan, las presentaciones las vamos a compartir, ¿cierto?
Sí, ya contaste esa pregunta.
Ok. I see it's actually saying it's not getting the OTP yet.
That's unfortunate. There's not much we can do about that other than try another email or stuff like that.
Yeah. Well, I will, I mean, that you can access them from every region. I mean, if you're in APAC, you can access them, but they are linked to a specific region. I will mention that in a while. If you're not getting the OTP yet, as Juan mentioned, try a different email, because yeah, it should be there. So try a different email address to see if that helps. Okay, so it is 11:08. So let's start. I was just checking on the chat your comments, but it is already time to get back to our workshop. So let me show the slides, because this is the last part of the lecture I am giving. So be patient. We will get to the hands-on part finally. This last set of slides I have here are to mention some of the Braket features and capabilities. So we saw an overview in my last slide, but here we're going to get deeper into it. Okay. So what does this service has to offer us? This is an architecture, a simple architecture diagram where we want to depict all the different pieces of the service and how the service interacts with the AWS ecosystem. So I will be zooming to each of these parts, and I will start by the central part, which I call the heart of Amazon Braket. So forgive me if I don't start by the components in the left. I will leave those to the end, because right after I explain those, I will be doing a demo to show you those components. So let me start by the piece in the middle, which is Amazon Braket Heart, which is the actual QPUs, and of course the simulators you can use to run your circuits before sending them to the QPUs. Okay, so we're offering these options. Obviously, the simulators are classical machines, but they simulate the processing that an actual QPU would do, given the code, the piece of code that you send there. Okay. And as I said, we're providing that because it will help you prepare your code, optimize it before using the QPUs, and therefore optimize your cost when using Amazon Braket. Actually, during the first year of usage of the service, you have a free tier that covers 1 hour of execution in the simulators for free every month. Okay, this is the first year of using Amazon Braket. You will have 1 hour of free usage of the simulators each month. Okay, now we have different simulators. We have actually 4 different types of simulators. The first one, we call it the local simulator, and that gets installed on your computer when you install the Amazon Braket SDK there. That is intended so that you start coding. If you want to work locally on your favorite IDE, you can do so. You can use your laptop, your PC, and run small circuits there so that you see how they behave. When I say running small circuits, is because local simulator is limited to 25 qubits maximum. So if you need to run a circuit that is longer than 25 qubits, you should go there and use the simulators. And also the local simulator will not will not do the processing in parallel, will not leverage parallelism. Which will actually happen in the rest of the simulators and in the actual QPUs. Okay, so that is also a limitation of the local simulator, but you have available when you install the SDK locally. Then you have 3 different types of simulators that will actually run on the AWS cloud. They are managed simulators. You just need to reference the resource name of each of them when you want to run the code there, and the code will go to the cloud, to the simulator, run on the simulator, and then give a response to you. Okay, The first one, we call it the state vector simulator, and you will see that we use a lot of short names in the AWS console. So it is identified as SV1. The characteristic that the simulator has is you can run circuits up to 34 qubits, and it will store the full wave function state of your circuit. What does this mean? And I don't want to, at these introductory sessions, I don't want to get into too much mathematical details, but what we can say, someone was asking about uncertainty. Well, yes, we have uncertainty when we process the quantum circuits. As I said, the quantum states are so delicate that even by observing them, we are affecting them. So what will happen when you execute your circuit is you will end up with a result that is digital. Let's say something really simple, that the result will be 0 or 1, digital. But during the processing, we will be able to use quantum states that are not digital and that are represented by a state vector. And this means that you have a behavior similar to a wave. That is why it's called a wave function, with some amplitudes and things like that. So using this simulator and passing specific parameters to your invocation of the simulator, of the execution in the simulator, you will be able to get the actual wave function instead of the discrete values that will result from executing your circuit. Okay, so that is a characteristic that this simulator offers. We will not be using that characteristic in this first hands-on we will have, because I will be just showing you like how to send your circuit to be executed here and get the final digital results. But there is a way in which, again, you can pass your circuit and then get back the state vector function, okay? The second one is the tensor network simulator. This allows you to program circuits up to 50 qubits. And the characteristic it has is that it represents your circuit as a graph. So the nodes of this graph will be the qubits and the gates you are applying on those qubits in your algorithm. And what this will do is it will try to find the best path to follow in the graph to execute the circuit. So it is a really good simulator when you are looking for optimization of your algorithm. And of course, the optimization will depend on the structure of the algorithm. If you have what is called local gates, so gates that are applied on a subset of the qubits, of the total qubits you are using in your circuit, then it will find ways to optimize it using the tensor network approach, okay? And finally, we have the density matrix simulator. And what this does is it starts introducing noise. And you will say, okay, why will we need to introduce noise? Well, because that is the actual way in which the real QPUs behave. So I was saying again that the quantum behaviors, the quantum properties are so delicate that they get affected by any interaction we have with them. So again, if we observe them, if we measure them, we are affecting the state. Also, the qubits has something that is called cohesion time. So even if we're not measuring their state, the quantum properties, let's say, they get lost in time. And when I say time, I'm referring to milliseconds. So they lose coherence in just a few milliseconds, and that introduces noise to our processing. That is why we need a simulator where we introduce this behavior that the actual QPUs will have, so that you identify how your algorithm will actually behave when you execute it in the real QPUs, and also so that you can start introducing strategies in your code to reduce the noise, okay? So these are our 4 types of simulators. And then we have the actual QPUs. And currently we have 5 different QPUs available through Amazon Braket. But you see here only 4. You will know why in the next slide. Okay, so these are let's say the first 4 QPUs that we made available through Braket, and they offer us different architectures, different ways they are built in order to represent the quantum properties in the qubits, and they offer also different programming models, so different ways of generating our algorithms. So for example, D-Wave, Rigetti, and OQC, all of them have the same architecture, which is based in superconducting QPUs. But IonQ has a different architecture. It represents the qubits using something that is called ion traps, okay? But then they have different programming models. So D-Wave uses something that is called quantum annealing. And someone was asking if we were going to use that. The response is yes, that is going to happen on day 3 of this workshop, okay? The rest of them use quantum gates. And today in our exercise, we'll start using quantum gates, okay? So these are different options. And the good thing is you will have all of them available through the same pane of glass of Amazon Braket. And also that you might be using the same SDK. If you program your circuits using the Braket SDK, you can run those circuits in the different QPUs. Of course, if you're using gates, you will not be able to run them using D-Wave. You have to use the different programming model there. But again, you will be still leveraging the Amazon Braket SDK, because otherwise each of these providers has their own SDK and offers their own consoles. But in this way, you have a unified way of accessing them. And also, someone was asking me if they are available from APAC region. That is also a good thing. I have heard that some of these providers, for example, in my country, are not available. If you want to use these QPUs directly with the vendor, those are not available from Mexico, for example. But using the AWS console, you can access them from anywhere in the world. You only need your AWS console and you will get access to these QPUs. Okay, and I said we have 5, but what you're seeing here just 4. That is because there is the 5th QPU was just announced. I think it has been already 2 months that it has been announced, one and a half or 2 months. And this is the Borealis processor from Xanadu. This Borealis processor, there was a big announcement for us because this processor it has been, there are papers that claim that it offers a computational advantage, the famous so-called quantum advantage over classical machines. So there is a certain use case that has been run on this processor that up to this point has not been run, has not been successfully solved and completed by a classical machine. Obviously, this might change in the future because we are learning a lot about quantum computing, but we are still learning a lot about classical, and we have a long road using classical machines. But at this point, there is a certain use case that has been executed here that cannot be completed by a classical machine, okay? And Borealis, again, offers a different architecture. This one is based in photonic qubits, and it uses something that is called Q modes. And it also uses a particular programming model that is called Gaussian boson sampling, or GBS. So it is not based on quantum gates, and it is used for particular use cases that might leverage the GBS technique. But again, it is available through Amazon Braket since, I think, 2 months ago. And finally, there will be a 6th QPU soon. This is already announced, and it is the Q-era QPU. And this one, again, we are adding more and more options here. So it will be based in a different architecture, which is the neutral atom qubits or Rydberg atoms. They are called so too, and it will use or it uses a programming model that is called analog Hamiltonian simulation. So more options available through Amazon Braket through a single pane of glass. And then this is the heart. I was telling you, this is the heart of our Braket service, the simulators and the actual QPUs, but it interacts with a lot of services that are part of our AWS ecosystem. If you have experience with AWS, you might already know some of these services. I explain them because maybe some of you are completely new to AWS, and also so that you know what is the value that they add to Amazon Braket. So the first one is CloudWatch, which is our monitoring service available on AWS Cloud, and it will monitor Amazon Braket. So it will help us monitor the execution of our code in the simulators and in the QPUs. It will, for example, if in your code you introduce some debugging messages, those can be available through the CloudWatch console so that you know what is happening with the execution of your algorithms. And of course, you will be able to build a benchmark on the performance of the execution using this service and comparing different QPUs, for example. And the next one is Event Bridge, and that service is used for automated notifications. So in this case, and you will see in a while when we are already in the hands-on, and when we send our circuits, our algorithms to the quantum processing units, the real ones, they will enter a queue. The QPUs have availability windows. They are not available 24/7 through the console. They have availability windows, but you can send your circuits anytime. So you can send them, they will be queued, and as soon as the QPU is available, the execution will be completed. So you can use Event Bridge to notify you of the status of your task and know when it is queued, when it is already running, when it is completed, and get automated notification through email, for example. So that's something you can do using Event Bridge. S3 is our object storage service. And what it will do is it will store the results of the execution of your circuits. So it will be stored as a JSON file, and I will show you that in a while. So you send your task, it gets certain result, and then it gets stored as a JSON file on Amazon S3. And it doesn't matter if the execution has already been completed, the file is kept there, and you can access it anytime, okay? Then we have identity and access management, which is used to control the access and the permissions on each of the resources that are part of Amazon Braket. So for example, if you have different groups of researchers, and you want each group to have access to a different set of resources, for example, each group will have their own Jupyter notebooks, or let's say there's a group that will only have access to the D-Wave QPUs, and other groups will only have access to IonQ and Rigetti. So you can control those permissions using the IAM roles in the AWS cloud. Of course, you can also control the access to the S3 buckets where the results are kept. And let's say be sure that only the right people is accessing the information that they should. And then we have KMS to do ciphering. I always forget this word in English, but to cipher the whatever is kept in Amazon Braket. For example, your Jupyter notebooks that are managed virtual machines on the AWS cloud, and you will be storing your code there. The storage of those machines can be ciphered, and you can use either keys provided by AWS or keys provided by you that are kept in this key management service, so that you make sure that your information is encrypted. That's the word I was looking for, encrypted and secure. You can also encrypt the S3 buckets where you will keep your results, the results of the execution. So you make sure that your information at rest is protected with the right level of security. Okay, so those are some of the main services with which Braket interacts. Of course, at any point you can use any other of the services that are available in AWS, but let's say that these are like the most typical and the ones that are more naturally integrated with Braket. Okay. And then I was telling you that I left at the end the left part, which is the interfaces that we have to interact with our Braket service. So of course, we have the Amazon Braket console, and I will show it to you in a while. We already accessed it, but we will have a look on the different menus we have available there. And that is that part of the AWS console that gives us access to particularly our Amazon Braket service. We have the local IDE, or let's say the Braket SDK, which, as I told you, you can install it on your own laptop or on your own PC and work from there to access Braket using the SDK, make your code there, send execution to the simulators or to the actual QPUs, which will happen on the cloud, but still you are working in your local environment of preference. And we have managed notebooks if you don't want to work locally, or if you need more resources because you are creating more complex algorithms. You can use these virtual machines that will be managed on AWS Cloud, and then that provide you environment that is already configured with the Braket SDK, with all the characteristics that are required to generate your Braket code and then execute it either on the simulators or on the QPUs. Okay, so that's it. And I want to mention something, sorry, about the SDK. First thing, Braket SDK is based in Python. So if you know Python, you have half of the way already there, because you will only need to be familiarized with the Braket libraries. And you can install it locally. There's the command. And it will offer, as I mentioned, it offers a local simulator where you can run circuits up to 25 qubits. You can use either the state vector or the density matrix simulator locally. You only need to add, let's say, an ID to your code that let the local simulator know which one is the one that it will be using. Okay. And you will have all the details of our SDK directly in our GitHub repo. And also in our GitHub repo, there are a lot of sample code and tutorials that you can follow to get started with Amazon Braket SDK. So I think Juan will share, or maybe he has already done so, the link to this repo so that you can have all the reference. And also, I think QML is on day 2. If not, Juan will correct me, but we will be talking about quantum machine learning. And in this case, what we are doing to leverage this differential programming approach is integrating with an open source library that is called PennyLane. Okay. So it is also based in Python, and it has integration with the Braket SDK. So you can use the QPUs available through Amazon Braket and do your QML algorithms. Okay. And finally, and we know that for those that are a little bit more experienced with quantum computing, maybe you have already used Qiskit, which is a development toolkit that has been there for a while. It was originally published by IBM, then donated to the open community. and it is really popular when we talk about programming quantum computing circuits. So we already have an integration with Qiskit, so you can take your Qiskit code and send it to be executed on the QPUs made available through Braket. Okay, so there's a plugin, you can do that if you are familiarized with Qiskit. Okay, so that's it for our Braket introduction. And at this point, we are ready for our hands-on experience. But before going into that, I will do a demo. And this is the part where I need you to be just observers. I know that you already want to put your hands on the thing, but please, please just, especially for those that are having your first experience with the AWS console and with Braket, pay attention to the demo I will do. I will show you the different parts of the console so that you know where you will find different pieces of information that are important to run your circuits. So let me share the browser. Okay, so this is the console. As we were saying, we have, I will show you the different menus here, the different options in the menu. The first one is new. It is something really new in our console, which is the dashboard. And here in the dashboard, the idea is that you have a single view of all the different parts, of all the different components that conform our Braket service. So for example, you have this welcome widget that gives you access to different links that are relevant so that you get started using Amazon Braket. You have also a view of your notebooks. So you have a single view of what notebooks you have active and available. The devices, you can set here your preferred devices. I will show you the devices in a while, but you can have them here as a quick view so that you can see there your preferred ones. And a list of jobs that you have recently executed. I don't have any because we haven't started to execute jobs or tasks, but you will have them there available too. And of course, you can customize it. Or you have the announcements. We're continuously publishing the news about Amazon Braket here, so you will have them here available. And you can customize this view, this dashboard, okay? Then the devices. And here you will find all the QPUs that are available through Braket. And as you see, for example, from D-Wave, we have different types of QPUs. For NQ and OQC, we just have one type of QPU. Rigetti is also offering just one because this Aspen 11 is not available anymore. And of course, the Borealis QPU from Xanadu. And you can see also the simulators here available. So one thing that is important, you can see here if those QPUs are available at this very moment or not. As I said, each of them has an availability window. I will show you how you can check on the details of the availability window. But in this single view, you can, from one side, see which ones are available at this very moment. Of course, the simulators are available 24/7, which is also a good thing so that you can test your circuits. So let's get, for example, into the details of the Aspen M2 of Rigetti. Okay, for each QPU, you will have a bunch of information here. Depending on the characteristics of the QPU, you will see information here. It varies because, again, it's different architectures, it's different ways of using them. So you will find different information when you access the details of each of the QPUs. Two important things I want to point out is the first one, the availability window. So you can see, for example, this Rigetti QPU has this availability window. It's available every day from 15 hours to 20 hours UTC, okay? This is one important part. The other important part you will see in each QPU is the Amazon resource name, the ARN. This is used in your code when you want to specify where you want your algorithm to be executed. So please be aware of this. I will be asking you to provide me the ARNs when we're doing the hands-on exercise, okay? Then we have, of course, our notebooks, and here you can see that I am sharing this account with 4 more people. We already have created our notebooks, and they are all in service. So these are virtual machines that provide us Jupyter notebooks, managed Jupyter notebooks, and that are already configured with a Braket SDK, so we can run our circuits there in the local simulator, or send those circuits to be executed in the simulators or in the QPUs, and we will be accessing them in a while. Actually, I will access mine here just to send a simple task to be executed and then show you the tasks option here. So I will be accessing here my Jupyter notebook. This is something we all will do together in a while for the hands-on exercise. But at this point, just check, and I will not take too much time explaining what I am doing here, because we will see that on the hands-on part in a while. I just want to execute a task. You can see that we have all
Could
the
you zoom in, Vanessa?
examples. We have here all the Braket examples that are available in our GitHub repo. Those are the same. So this Jupyter notebook instance is already populated with all those samples if you want to start from there. We'll get into the getting started is, and I will get into this simulators notebook. And again, I will not take a lot of time explaining this, because I just want to run it so that we have a task that I can show you in a while in the tasks menu. Okay, don't worry, because we will check our code in the hands-on exercise in a while, step by step, so that you see how to run your circuits. I'm just doing this so that I have, okay, we'll jump to the on-demand simulators so that we have one task to show in the console. Okay, it's been executed. So just using, okay, but I think it's been executed already there. Okay, yeah, and just to print the result and the task summary. Okay, we are fine. So we should see, if I go to the tasks, we should see the task that I have just sent to both simulators, the state vector and the tensor network simulator, which is what that notebook covers. And here, I mean, in this task menu, you will be seeing your task appearing in a while. When we are all executing the notebook, you will see a lot of tasks here, because there will be the task from all the people that is sharing the account. At this point, you can access any of the tasks if you want when we check the results. But if you want to access your own task, the ones that you will be sending, you will have to take note of the task ID. I will let you know at which point in the code this will appear, and you can take note of that. But what you can do from here is obviously access the bucket, the S3 bucket, where the results are kept. So you go directly there. It will take you to the S3 console, directly to the results of that task that has just been executed. And as I said, it is a JSON file, which you can use later on to process, to analyze the results of the execution of your task. And I will just access it here so that you see that we can check it directly from the console if we click here, open. Okay, we'll just open it here with, I think I have Sublime Text. So you see that I have here some JSON, okay, some JSON structure with the results of my execution. It will make more sense later on when we see the circuit that we are executing and why we are getting so many ones and zeros here and there. But that's the idea, that you know that you can navigate directly to the S3 bucket where the results are kept from the tasks menu, clicking into the task ID and then going into the results. Okay. So that's it. I will go back to the Braket. Sorry. The Braket console here. And we are ready to start the hands-on. But what I want to do before that is briefly explain some basic gates, because we are going to be using those gates in our exercise. And especially for those that are just starting with quantum computing, it is important that you visualize what we are doing here, okay? So just a couple more of slides. Okay, here. And for this, the first gate that I want to explain, one of the basic gates we have is a poly-X or NOT gate. Okay, it is a single qubit gate. I'm calling my qubit A. That qubit can have an initial value of 0 or 1. Okay, we're going to start thinking of it digitally. Later on, we'll add the quantum properties, but at this point, let's think of it as a digital values, 0 or 1. And the effect that this poly-X gate has is that it will, let's say, if we have a 0, it will change it to 1. If we have a 1, it will change it to 0. It's like a regular NOT gate in the digital world. If we give you more details on the mathematical part of this, each quantum gate is actually a matrix. So you will take the vector that represents your qubit, and you will do some operation with this matrix. In this case, you will multiply. So the poly-X gate matrix is a 2x2 matrix. In the first row, you will have a 0 and a 1. And in the second row, you will have a 1 and a 0. So you take that matrix, you are going to multiply it by the state vector that represents the qubit. And the effect it has, it switches amplitudes of the state. So let's say we have a sphere. Commonly, it is common to represent, I don't have a sphere here. It is common to represent the qubits with a Bloch sphere. So let's say this is my sphere. Imagine this is a sphere, and this is a vector. This vector represents my qubit. If it points to the top, it has a value of 0. If it points to the bottom, it has a value of 1. So if I apply the poly-X gate and I'm switching the amplitude 180 degrees, if my qubit starts with 0, I switch the amplitude 180 degrees. That is why it ends up as 1. That is the effect of the poly-X gate, and that is why we can see it as a regular NOT gate in the digital world. Okay, so I have my table here of results. If I have an input of 0, what will I get after applying the poly-X gate? Just to make sure we're all in the same page. If I have a 0, what will I have as the output? If you can just chat. Just explain with her hands. Yeah, it was okay. We're going to get a 1. Exactly. I see a lot of 1s there. Okay, that's right. If I have a 1, and I apply the poly-X gate, what will I have at the end? A 0. I have a lot of zeros there in the chat. Okay, that's fine. That's simple. Okay, and we're still like thinking digitally. Okay. Then we have this other gate that is called the control NOT gate or C-NOT gate. And it is called controlled NOT because we have a control qubit and a target qubit. And again, I am representing them here as A and B. A will be my control qubit. graphically, the circuit is represented by this. The control qubit is like just a point. And I have a target qubit, which is represented here as a circle. The control qubit, depending on its value, it will have an effect on the value of the target qubit. So if A starts with a value of 0, my target qubit will remain the same. It doesn't matter which value B has, it will remain the same because my control qubit has a value of 0. But when my control qubit has a value of 1, it will an X gate will be applied to the target qubit. So we will have this amplitude shifting 180 degrees. Okay, that is what happens when my control qubit has a value of 1. I will apply a NOT or an X gate to the target qubit. Okay, so let's see our table. The first row, my control qubit has a value of 0. And my target qubit also has a value of 0. What will be my output? What will be the value of A and B at the end? Who can tell me? I have a 1 there. I'm not sure. Remember, when the control qubit has a value of 0, I will do nothing. 0, 0, I see there. That's true. So my output will be 0, 0. I will do nothing. Okay. Second row, my control qubit has a value of 0 again, but my target qubit has a value of 1. What will I have at the end? Okay, I see a 0, 1 there. That's true. Because I'm doing nothing. The control qubit has a value of 0. I'm doing nothing. Okay. Perfect. Then, okay, someone is getting ahead. Please be calm because I want all of us to have an understanding of this. Okay, in my third row, I have my control qubit has a value of 1, and my target has a value of 0. What will I have at the end? 1, 1, that's true. Remember, when control qubit has a value of 1, I will apply a NOT gate, an X gate, to the target qubit. So I have 1, 1. And the last one, if I have a control qubit with 1 and a target qubit with 1, okay, I have a 1, 0. That's true. So I think we're all there. And again, what we have here is still digital, okay? It's still ones and zeros. So let's introduce superposition, one of the most important and basic properties in quantum computing. So superposition means that we are going to have a combination of these basic values that are 0 and 1. We can combine them to be a little bit of 0 and a little bit of 1 at the same time, right? So it is a combination of both my basic values, my base values. So in order to put a qubit in such a condition, a superposition, generate a superposition behavior, what I use is something called the Hadamard gate. The Hadamard gate has this result. Okay, if I start with a 0, it will have at the end this result. And if I have a 1, it will have at the end this result. How does this happen? I was telling you that the quantum gates are matrices. So the Hadamard matrix is, again, a 2 by 2 matrix. The first row we have a 1 and a 1, and the second row we have a 1 and a -1. And all the matrix is multiplied by a coefficient that is 1 over the square root of 2, okay? So that is why we get to this result, by multiplying our state vector of the qubit by that matrix, which is the Hadamard gate. Okay, and again, if I have my glockenspiel, just to have it visually, it helps me have it visually. My vector, again, when it points to the top, it is a 0. When it points down, it is a 1. When I apply the Hadamard gate, what I am doing is I am rotating this vector in such a way that it is located, let's say, in the equator of the sphere. So it's pointing like in the x axis, okay? And since it is in the actuator, it has exactly the same probability to end up being a 0 or a 1 when it collapses. When I observe its state and it collapses to the base states, to the base options, to the base values, okay? So that is why, that is how I am generating a superposition state with a combination of the base values, which are 1 and 0. And why, when it starts with a value of 1, it has a minus here? Because the rotation points to the x-axis, but to the back, let's say, to the back of the sphere. Okay, that's the effect. So I am generating, again, a superposition state. For those that are just starting with this, I'm generating a superposition state with a Hadamard gate, where I have the same, exactly the same probability to end up with a value of 0 or 1. 50-50 probability. Okay? Remember that. Because we're going to combine our gates here. So we have this circuit, that is the one that we will be executing in our exercise, that is called the bell pair. And the bell pair generates it creates an effect that is called entanglement. It's the basic entangled state in quantum computing. Entanglement means that two or more qubits will be related in such a way that when we affect one of them, the other one will have an impact, okay? So to generate this basic entangled state, we are going to use a Hadamard gate. Remember, the gate that helps us generating a superposition state, and then a control knot. And to have an idea of the effect of executing this circuit, let's say that both my qubits start with a value of 0, okay? So if I start with 0, 0, I have a Hadamard gate on the control qubit, and then I have a control knot. What are the values that I will get at the end? Who can tell me? I start with 0, 0, Hadamard gate, CNOT gate. Who can tell me what will be my output? I want to see your responses in the chat. So remember, you're having a Hadamard. You have the same probability of ending up with a 0 or a 1, and then you have a CNOT gate. I have a 0, 0 there. That's a part of the response. That's true. I have a 0, 0. That's part of the response. But remember, the Hadamard, yeah, I have the response. The Hadamard generates a state of superposition where I have the same probability of ending up with 0 or 1. So that's true. I will have a 0, 0 as an output. But I will have the same probability of ending up with 1, 1 at the end because of the Hadamard gate. Okay? So that is what why we were saying that the results in quantum processing have certain level of uncertainty. They are probabilistic. When you run a circuit, you should run it a lot of times, which are called shots. And at the end, you will receive a probability of getting certain result. Okay? In this case, we should be closer to 50% of probability getting 0, 0 and close to 50 getting 1, 1. Okay? And this is the mathematical expression of this result. And the other circuit that we will execute in our exercise is called the GHC, or Greenberger-Horn-Zeilinger algorithm, which is just a Bell state, but with a lot of qubits. You can add as many qubits as you want. You will apply Hadamard gate on the first one, and then you will apply a series of CNOT gates pairing the qubits one by one, gradually, okay? And it has the same effect. If you have n number of zeros at the end, you will have the probability of ending up with n number of zeros or n number of ones. That's the only effect of this GHC circuit that you will see how it executes now that we go into the hands-on part of this. Okay, so hopefully I have created an idea of how these basic gates work in your minds, and now we're going to put our hands on the stuff and see this in reality. Okay, so let's go to our console here. Okay, let me get out of the presentation because otherwise you're not going to see. So all together, we're going to execute this all together. Okay, let's go to our console. Let's go to the notebooks part. And each of us will access their own notebook. Please access your own notebook, because otherwise you will be modifying the notebooks of the other people and this will be messy, okay? So I will access mine here. And you can get into the Braket examples folder and we will put here a code that I will provide. So, okay, let me check. I think you sent me the link in my email, Juan. Or do you send it in Slack? I don't remember. Let me check. No. So I should have the link here somewhere. Let me check.
Sorry, I was on mute. I'll share it with you. Apologies.
Or have you shared it in the WebEx?
I was about to do that. Sorry, I thought I did already.
Let's do that, and I will take it from there.
Okay.
So we will all get a link that Juan will share, which has the code that we will be using in this first exercise. And
it's coming, guys. Just give me a second. Sorry, I thought I did it before. Here it is.
I'm sorry, because I know you sent it to me, but
Yeah. That's not very useful, right? If I only send it to you, I need to share it with the audience. There you go. That's the link.
There we have it. Okay, so let's click on that link. I will do that here too to get the code that we will be executing now. You can save it. I will save here in my desktop. And once you saved it, just let's uncompress the file here. Okay, and you should see something like this. It is a Jupyter notebook, and then it has a couple of images that are loaded into the notebook. Okay, so let's get that zip file. Let's uncompress it and have it available. And now we are going to upload it to our Braket examples folder here. So let's go to the upload button here in the interface of your Jupyter notebook. And you're going to select the files, the 3 files. Okay, here I will select them and click open.
Are you sharing your screen, Vanessa?
I think I'm doing it.
Okay, so it must be just me. I'm not seeing anything.
Are you seeing my screen, guys? Or okay, yeah.
Sorry, apologies. It's just me.
So, how to copy that zip? Can I show it again? Okay, just go into the. I'm sorry, I will hit cancel here. Go into the link that Juan provided. Once you're there, it will ask you if you want to open it or save it. I have saved it to my local disk. Please do so you can keep the notebook and use it later in your own AWS account. Because remember, these accounts are temporary. So keep it. We're going to uncompress it. I already did so, and you will see that it has 3 files inside. Once you do that, you will go to your Braket examples folder here in the interface of your notebook, and you will hit the upload button here. So go to the folder where you uncompressed it, and you will select the 3 files. Then you will hit the open button here, and you will see this. Hit upload here to the 3 of them so that we have our notebook fully loaded into our Jupyter instance. If you're already there, you will see this Amazon Braket Hands-on Lab Day 1, August 22 Jupyter Notebook. And you can click on it to open it. We will start executing our notebook. We will start executing circuits on Amazon Braket, okay?
Here's the annoying guy again asking you to zoom in a little bit, Vanessa. Sorry.
Oh, really? Because I'm seeing it as a really big.
Some people have very small screens, so just can fit it
Okay.
as much as you can. It's fine. Perfect. Thank you.
Okay, so we have our notebook here. Let's go executing it all together. I will be explaining the different parts. So in the first part, we have some imports of the Braket libraries that we will be using. And you will see some imports later on because I am importing only those libraries that I will be using in each piece of the notebook. You will see that you don't have to import the whole thing. As always, you are optimizing your code, so just import the modules that are required at every piece of your code. So let's run this just to get the imports. And then, well, this piece is just to load the image. So we have an image here representing our bell state, which I already explained. So I hope you already identified our circuit with the Hadamard gate and with the control NOT gate here. So let's build it. Let's build that circuit in our code. It is as simple as invoking the circuit object and then sequentially adding our Hadamard gate on the qubit 0. Remember, the qubits are like an array of qubits. So when we reference qubit 0 is this one that appears in line number 1. Okay, so we're going to apply the Hadamard gate in our qubit in the first row. And then we're going to apply the control NOT gate, defining that our control qubit will be the first one and the target qubit will be the second one. That is what this line means. This line is the one that where we are building our circuit. Okay. Can we get the recording of this session? I think you will get. Juan is recording it, so I think it will be shared. And where we will let you know. Be patient. Okay, so this is the line where we're building our circuit. Okay, as simple as that. I will uncomment this print line because I want you to see how this bell circuit that is built here can be printed. So let's run that. If you uncommented this, you will get the graphical representation of the circuit you just built using this line. Okay. And then what's the step after uploading the files? You just need to click on the Amazon Braket Hands-on Lab Jupyter Notebook, and it will take you here. And then you will start executing each piece along with me. Okay. So this is the graphical representation of our circuit. And well, we have an invitation here so that you can check the developer guide and check other gates that are available through the Braket SDK. Okay, but we are just using those gates at this point because it's our simple initial circuit. Okay, now let's send that circuit we have already built to be executed in the simulators. First one is we will run it on our local simulator. In this case, the local simulator will run on our Jupyter instance. It is local, but it is on our Jupyter instance. So let's go run this. What it is setting, as you see, the device to local simulator. Then it just runs with this line, it runs our Bell circuit on that device. And then using these counts, we will count the measurements that it gets after execution. Okay, so let's do that. And you will get something like this. As we were saying, we should be close to 50-50% of possibilities of getting 0, 0 or 1, 1. Okay, I was seeing circuit is not defined.
We got that one fixed, Vanessa. Don't worry about it.
Okay.
I will keep answering in the chat.
Oh, you're okay. So just to mention, you see these shots 200 because as I was saying, since our results are probabilistic, we have to execute our code, our circuit many times to know how many times the execution will get the 0, 0 or the 1, 1. So we're setting our number of iterations to 100. We can change this. We're leaving it to 100 at this point, but that is what the shots mean. So at the end, of course, 52 plus 48 will give you 100. That's the number of times it was executed. Okay, yeah, you will get, obviously you will get different results. It will vary, but it should be closer to 50-50, okay? And then we just go and plot our results. And we see this graph that shows us that it is really 50-50% of times getting 1, 1 or getting 0, 0, as we explain in our slides. Now, let's create our GHC circuit, which you might remember, it is just a Hadamard gate on the first qubit and then a series of control node gates on the rest of the array of qubits. So I am adding here a little bit more of the Braket SDK modules just to be able to complete my GHC circuit. And here I have the piece of code where I will build the circuit. How it works. Again, we are defining here a circuit. We are adding our Hadamard gate on the first qubit in our array. And then using this cycle, this for sentence, we're going to gradually add the CNOT gates on the consecutive qubits that conform the array. So in this case, we're just building it. In the next step, we're defining the size of the array and invoking this function, okay? But this is how we're doing it. Instead of going manually adding the CNOT, 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 we are doing it inside a for statement, okay? So I think I didn't run that, sorry. Okay, let's just define that function. And then here, we're going to define the size of our array. Here we have 5, I will change it to 20. Please try to keep it around 20 because as you know, we have certain limitations using the local simulators. We don't want to go above 25 at this point. Just keep it as 20. And let's invoke the build of this circuit. I will again uncomment the print here so that we can see the circuit that has just been built. And you see I have this array of 20 qubits that are sequentially applying the CNOT gates to generate our GHC circuit. Okay. And then, well, this is just to load the image. This is what we are creating. Okay. So we have already our circuit. Now let's send it to be executed to the local simulator. And I want your participation here. We already have these lines in our previous steps. So what is the line in which we will set up the device to be the local simulator? Who can provide me that line in the chat box? which is the line of code. Okay, you have it there. It is the one that says device equals local simulator. So let's take all of that line and add it here. Device equals local simulator. We are setting there the execution to be run in the local simulator. Let's run that. Then how we're going to run our circuit on the local simulator? Who can provide me that line? Again, you have it in the previous example. There you have it. Okay. But you see you are referring there to the bell. I think we called it differently here. We call it GHC. Remember that? Okay, so let's have that line. Yeah, some of you are already sending it to me with the GHC reference. So let's paste it here. There we are running. Oh, sorry. I'm trying to copy it to avoid moving in the notebook, but I am not getting it. There we have it. Remember putting GHC here, otherwise you will be still executing the bell circuit we defined previously. So let's run that here. Okay, then how we're going to get the measurement counts, the measurement shots, sorry. Okay, there we have it. Let's set our counts variable for measurement counts. I will copy it from here. You are doing it very well. I'm sorry. It is not getting copied. Okay, there we are getting our measurement counts. Let's run that too. Then let's print the counts. So, okay, just print counts. That's true. Let me see if it allows me to copy it here. Print counts so we can see our results. And we should expect or have a result of all zeros or all ones with the same probability. There you have it. So again, close to 50-50, we are going to get our 20 qubits as 0 or our 20 qubits as 1. Okay, I have someone that run it with 5 qubits. That's okay if you didn't change the value. Oh yeah, but you get a 50-50 exactly. That's an amazing result. Oh, good, 73-37. That was strange. Sometimes it happens, I must say. Okay, someone changed it to 1,000 shots. That's amazing. Very well. Why GHC, you're asking? Okay, because remember we defined our circuit with this function in which we added the Hadamard gate to the first qubit and then gradually the CNOT gates to the upcoming qubits in the array. And when we invoked that function, we put the result in this variable called GHC. So this is the one that is referencing this circuit that has n number of qubits being entangled. That is why we use GHC here in our device run sentence. Okay, fine. Okay, now we're working with simulators, the local simulators. Now let's send it to the simulators that are available in the AWS cloud, the managed simulators. In order to do so, look at this. I will change my device line to reference the ARN of my managed simulators. This one is the Amazon resource name of the SV1 simulator. Okay, remember I showed you in the console how to get that. We will do so in a while for the QPUs. But this is the way we specify where we want our circuit to be executed instead of the local simulator. So let's run that. Again, we have here all the lines that we already checked that will help us run the GHC circuit. In this case, we are running 1,000 shots. We are running a circuit with 20 qubits. It's already there. And we will be running this in our recently defined device, which is one of the managed simulators.
Just a time check, Vanessa, you are over time, but I can give you another 10 minutes if you want.
Okay.
Yes,
let's at least close this and one QPU, and the rest of the notebook will be left to you as homework. So we already, okay, we run that. So we're getting our zeros and our ones close to 50-50 here. And it is important when you run this on the managed simulators or on the QPUs, in order to track the results, you will need to recover the task ID. That is what we will be doing with these lines. Okay, remember I showed you in the task menu that you will have there the task IDs, and then you will be able to get there and get the results in the S3 bucket. So if I run this, I will have here my ID, my task ID, which I can then use to keep track of the execution and of the results. Okay. Well, I will not execute this step. It will be set to you as homework because we are over time, but here you can change this line and set the resource locator of the TN1 simulator, and again, run your circuit there. Then let's go to running the task in one real QPU. And for this, I will add another library here, another module. And I will ask you here, let's define our device. I will ask you to provide me the resource name of the Rigetti QPU, the available one. So please send me in the chat the resource name of the Rigetti QPU. No, that's a TN1, that's one of the simulators. I want, okay, the Rigetti QPU, there you have it. Julia has just sent it. That is the available one because there's another one, but it's not available. So I will take it from here, and here you will replace that value. Here I'm referring to the Rigetti QPU. So I'm saying that this circuit will be executed on that processor unit. Let's send it there. And I have here my task. Remember, this task ID is not given to us by default. We have to recover it. So that is why we're using these lines. And with this, we will be able to keep track of the execution and of the results. That is what we are doing here. Let's print the status. It says running. Remember that it can get a status of queued. It can say running. It can say completed. So depending on, okay, so now if I run it again, it says completed. And then with this task recovery code, I can get the results of the execution in the Rigetti QPU. And you see that I'm not getting all zeros and all ones. I'm getting a lot of different results with different probabilities. Why is that? Who can tell me? The resource name, I can get it from the devices option in the menu. You get into the details of the device and you will find there the area. Noise, that's true. That is what happens with a real QPU. I get noise introduced. That is why I'm not getting all zeros and all ones, because noise is introduced. And I will leave the rest of the exercise for you as homework, so you can run your circuit on IonQ and on OQC. Since all of them are based on gates, you can use the same circuit code that we defined in order to run it there. And with Juan, you are going to check about this noise that we are detecting here. Okay, so that's all for me. Thank you very much.